Buongiorno. Good afternoon. Thank you very much, Giorgio. I'm very honoured to be here and to be asked to speak. And thank Giorgio and the organising committee for this opportunity. I also congratulate Giorgio and the organising committee on this highly successful Congress. So this afternoon, I'm going to talk to you about how our roles as engineering geologists in communicating engineering geological data and information is evolving and changing, and how we can now communicate this information. Working at the British Geological Survey, this is extremely close to my heart. It's part of my day job, but an ever-increasing important role in what we do in the survey. In this talk, I'm going to present to you how we used to communicate geological and engineering geological information in the past, and then talk about how we have new ways to deliver that and the challenges associated with that, and then a few summary thoughts about some of the challenges we have in the future. As an engineering geologist, we communicate our knowledge through the interpretation of geological, engineering geological, geotechnical information in maps, models, and graphic logs. And even, as you can see, some of the old-fashioned block models that we use to help us. From William Smith's first geological map to the more modern paper maps and our digital maps we now have today, there were a variety of scales that we actually can present this data at, from the very large-scale, site-specific maps to the very small-scale regional and national engineering geological maps. Small-scale maps like the one shown on the slide that was created by John Dobson in 1836, when an extension to one of my hometowns, Newcastle upon Tyne up in the northeast of England, was developed and expanded. And that's the quayside there. On his map, he put down the locations of borings and information about the depth of those borings. Moving on, of course, then to William Smith's first map, which was a national scale map. Of course, we also present data and information in the many technical reports, raw and geological and engineering geological information, geotechnical data and information, logs, geotechnical laboratory data. And in the past, we provided these mainly to civil engineers to help with the design of structures and buildings, but also occasionally to planners and builders. As engineering geologists, for many years, we've tried to provide informative, relevant and useful information in the form of interpretive maps. And here's just a few selections that came from examples that were presented in Bill Dearman's 1991 book on engineering geological mapping. An example from Prague at a 1 to 5,000 scale that's looking at the location of superficial and bedrock with the indication of where you could actually excavate and build. Down to the BRGM 1972 map from France, from Creel, that looked at foundation types, a very different and very 1970s digital selection of dots. And then an example from BGS that we created from our applied geological mapping program of Bradford, where we presented a mixture of geohazard information and ground information to help planning. So since William Smith's first urban map that was developed in Bath in 1799, the way we've produced and represented information has not changed for many years, until probably the last 20 years or so. And in that last 20 years, we're now engaging with a much wider community. And that community are now wanting different and relevant information. Many of that community don't have geoscience backgrounds, and we're now having to think of different and imaginative ways to present our data. So, communication challenge number 1. Advances in information technology in the last 20 years has enabled greater computing capacity, and changes in software and technology has transformed the way we've started to look and analyse at geoscientific information as well as engineering, geological and geotechnical. In particular, over recent years has been the development obviously of digital maps and data from our well-known ArcGIS into using modelling packages. This has given a wider aspect of the way that we present our data and information, from web mapping services online that people can access, as you can see from the Geology of Britain viewer, to apps and applications on your iPhone, to digital remote computing that we can take out into the field and take with us all the relevant digital, geological, remote sensing, topographical data, and enabling us to interpret things directly in the field and take it back into the office and use it fast and efficiently. But we're also still creating the interpretive maps by using a multitude of data and information in GIS information systems, being able to combine GIS layers, both geological and geotechnical information, to be able to produce things like the Engineering Geology map of the United Kingdom, and also now available online through a web mapping service. But other techniques we are now using, again, GIS systems to help develop decision support tools, so we can incorporate remote sensing data, geological data, other relevant topographical, national public data sets such as population databases or land use, to enable us to provide best available information and data for non-specialists to use and make decisions. And this is an example of an EU project that's just finished called PanGeo, where geohazard data and information has been combined to help city planners to understand the potential hazards that could be there in their cities from geohazards. And of course, one of the biggest changes has been in how we look at 3D geological data, geotechnical data, and how we model that. This has revolutionised the way that we look at geological information, particularly in the urban environment, and has enabled us to look at incorporating both geological, geotechnical, remote sensing data, and being able to combine these into information sources that are relevant and useful. A variety of software are now used from this. This is just a few that I know. GoCAD, creating geological surfaces, modelling faults. GSI 3D, something that we use in-house at BGS that enables us to model particularly well superficial deposits. And then moving on to the more geostatistical techniques, creating voxel models to enable physical properties, whether they're geotechnical or petrophysical properties, to be able to be viewed and analysed. And certainly the work that's just been published in the bulletin from IAG Commission C25, the use of engineering geological models, has just prepared a good outline and guideline to the use and an introduction to the use of geological models for engineers, for engineering geologists, sorry. But there are lots of different ways to create these models. Some of them more complex than others, some of them more time-consuming than others. We have different techniques now, and two of the techniques that are particularly being used more are deterministic modelling techniques, which are expert person-driven. They're quite time-consuming and mean that you end up with the input being the exact determination of the geologist or the engineering geologist involved. or the more analytical, statistical and stochastic models, which I'll talk about more directly in a moment, that are mathematically driven, estimating probability distributions and allowing random variations from historical data to be analysed and visualised in a number of iterations. So deterministic modelling enables you to incorporate, as a geologist and an engineering geologist would, all the available information to create your observational engineering geological model, from maps, from digital terrain models, using boreholes to interpret cross-sections, to create fence diagrams, block models, and your layered 3D model. These are very labour-intensive. Certainly the techniques we use in BGS need a lot of intervention, and as a result of that, very challenging, certainly in the Geological Survey when you're trying to map the whole of the UK. More and more people are looking at analytical techniques such as geostatistical ones, and certainly through the work we've been involved with, creating stochastic lithological models as one example. And this is a project that was undertaken, an urban project in Glasgow, up in Scotland, where we used historical borehole records and we had lithological information for 500 different points, which we used to actually help iterate variations on simulations for the model runs. These were all based on lithologies developed around Eurocode descriptions and enabled us to look at the spatial variability of the lithologies at a given location. Of course, when you have these models, one of the best things is you can then interpret the model, slice, cut, splice. And the benefit of these particular stochastic models means that you actually know the depth and the amount of variability of certain lithologies at various locations. Something that's very useful if you are, for example, wanting to put a foundation down. So deterministic versus stochastic modelling. This enables you greater lithological variability to be identified. Deterministic, as I said, is more time-consuming, but it has that expert intervention and knowledge that can be interpreted in when you have lack of data. The stochastic model captures the variability in the lithological information, but requires high quality and large amounts of data to be looked at, but allows reliability and uncertainty in the data to be looked at. And certainly in the next example, where you can actually start looking at some geotechnical properties, density for example, where we modelled density from the top of, the base of made ground to the top of the bedrock. And these geotechnical properties then had lithological variograms created for each lithological classification. And of course, from the variograms, you can actually see the statistical variability of the data we have. These data are then generated and created into multiple simulations. And this is of bulk density in Glasgow. Big challenge with the Glasgow data. This is all around superficial deposits. They're spatially very variable. And this technique actually enables you to interrogate that based on the data and the quality of data you have, though. And allows you to get a subsurface understanding which you can then analyse in cross-sections. Multiple iterations in simulations. This is for 10 simulations. This is for 100. There is one thing, though. This method may not be suitable for all parameters and is highly dependent, as I've said before, on the quality and the quantity of data and the distribution of data, of course, the spatial distribution. And, of course, works very well in a very densely data-populated area like Glasgow. But the benefit is we can look at some of the statistical values, such as mean, standard variations, just as a few. And it helps us to look, of course, at reliability and uncertainty in a quantitative way, and highlight areas where further ground investigation will be needed to improve the data and allow further simulations to be generated. Once you have information on these geotechnical properties, additional data can be derived using characteristics. And this is just one example, using a characteristic that we derived from some research up in the northeast of Scotland, where we looked at the relationship between bulk density and hydrological conductivity. And using this spatial relationship that we created, we'd then be able to make another iteration of the model, and enabled us to get the hydrological conductivity model, this based on 500 data points with 500 simulations, subdivided again by the lithologies. Our hydrogeological colleagues are using this data now to help them improve their understanding of the spatial variability of the very complex environment, hydrological environment in Glasgow within our superficial deposits there. So this just gives a very, very simple overview and workflow for looking at modelling in urban areas. And using these methods, whether deterministic or stochastic, based on the sort of data and information you have, and that has to be assessed, you can actually start looking at lithological variations, geotechnical or geophysical properties, for example, to develop voxelated models that give us an idea into the uncertainty around the reliability of data. And these data sets are starting to be used actively in Glasgow by Glasgow City Council to help them guide in their development and planning. So, communication challenge number 2. Different types of digital engineering geological information is becoming increasingly available for larger areas. I'll put urban in there for the examples that I'll use in a minute, rather than just for site-specific. IT is now enabling us to make these simulations more efficiently and effectively. It's important, though, to ensure that engineering geological observational models are incorporated, though, with other data and information about the underground, especially when we are now being actively encouraged in many countries to use initiatives such as building information modelling. And that is now changing how buildings, infrastructure and utilities are planned and designed, built and even now apparently managed. As the engineering geological community, we need to engage with this and make sure this information is incorporated and, most importantly, used. This example that's shown in this fly-through is an example from the northwest of England, where a 3D deterministic model is used to look at the spatial vulnerability of the sewer network if it failed, to potentially contaminating the underground reservoir. And by using the 3D model, we've been able to make simulations that then again give us very detailed areas of potential vulnerability maps. And these have been effectively used by the utility sector in northwest England. So, we've had a little fly through northwest England, but now thinking about 3D models, more and more 4D simulations and the generation of 4D temporal monitored data is being used in many large engineering projects. And these are being generated on a regular basis, where an important understanding of particularly the 3D property model, geotechnical property or geophysical, This is actually an example of a 3D geophysical property model, which uses resistivity to monitor an engineered embankment. The engineered embankment, for this study, it's important to understand where the potential areas of increased moisture content can be. So if there's a potential for that area to fail, they can be highlighted. And this is a real-time active monitoring system that's active on an engineered slope not far from our offices at BGS. But the challenge with this 4D temporal data is that creating the models are quite labour-intensive. Doing the iterations of the interpretation between the 2D property modelling and creating that into a simulated real-time 3D temporal data is labour-intensive, potentially, and very data-hungry. Although when you present this sort of data to particularly asset managers, they get extremely excited. But there's a lot of investment that's needed to do this, and the visualisation and development of these for engineering projects is ongoing at the moment. This spatial data and information, though, is now allowing better engineering decisions to be made, particularly on embankments like this, to ensure that asset management through monitoring is timely and appropriate maintenance happens. And to ensure, of course, that the geotechnical risk associated with that is better managed and efficiently managed. But of course, with all this generation of data and information, the most important thing is to, and it's vital, to ensure that good data is used in the models and that data is well maintained. So best practice and standards are absolutely vital here. AGS is one of the standards that's certainly been adopted in many countries to deal with geotechnical data. And this is used particularly in the UK, Hong Kong, Singapore, UAE, and the US at the moment are developing a similar system called DIGS. These ensure best practice, they ensure that Eurocode standards are maintained, and they also maintain that data is reusable and interoperable, which ensures that ground investigation data is not just used once, but many times. Again, back to Glasgow, this concept of AGS data transfer has been taken a lot further. The BGS have worked very closely for many years with Glasgow City Council, developing geological and engineering geological models, data sets and inventories. And what we've now started to do is ensure that data between all bodies working within the ground investigation community within Glasgow are sharing data and fostering partnerships to ensure that subsurface data and information and knowledge are transferred throughout the working stakeholders. This has set up what's known as the ASK network. At the moment, the ASK network has 25 members and 3 supporting organisations, one being, of course, the AGS, but Scottish Government and also the Soil and Groundwater Technology Association. At the heart of the concept of this network is a more collaborative approach to subsurface data and information. Sharing the information and ensuring that the relationship between all organisations is open and enabling data particularly, and I'll reiterate it one more time, can be reused by all parties that work within the Glasgow area. To ensure that data in Glasgow can be reused and transferred, a specification based on AGS has been designed specifically for Glasgow by Glasgow City Council, BGS, and with communication between other stakeholders within the community as part of the ASK network. GSpec gives us a specification for data capture to ensure data is improved, reused, and most importantly, it comes in the right format, not paper anymore, but digital format to enable efficient and effective incorporation into long-term national data sets. But also key is it can be reused by all parties because it has the appropriate metadata as stipulated by AGS to be reused and transferred between different data packages. But of course, to facilitate that and ensure that this is done, two things have happened. At the moment, there's a demonstration portal that has been developed, and Glasgow City Council now are making it mandatory that all their procured ground investigation data has to follow the GSpec format. And through the encouragement of the GSpec Portal, which is now being tested by BAM Ritchies and Scottish Water at the moment, the idea is to encourage people to do that themselves. This has also been taken up by a wider European group known as Suburban. This is a group that have been funded through an EU grant called the Cost Action. It facilitates knowledge and exchange and development between different countries within the European Union. And particularly a couple of progressive cities are now involved in this to share knowledge and the way that European cities share data and information for the subsurface. And particularly at the moment, there's been knowledge exchanges on groundwater data in Hamburg and Odense in Denmark. And this is ongoing at the moment and will finish in about 18 months' time. So the final challenge I want to talk through is actually ensuring that engineering geologists are working more in partnership with stakeholders and also working with social scientists to improve how we communicate engineering geological information. Now, the last couple of examples I've given you from Challenge 2 really indicate that that's happening through some of these initiatives right across the engineering community and ground investigation community. But also just to pick up and highlight another community that is starting to work, and we've heard a lot about that during this week, is communication of basic geohazard information. Increasingly more, the general public, the newspapers, certainly in the UK, the wider community and the responder community, the blue flashing light, police and fire service, are actually wanting more information on these geohazardous events. They're wanting simple information that is understandable to them, is easily accessible, and explains to them what these are, what it means to them, and what do they need to do. And the example I've shown here, just to illustrate that, is something that we're using in the UK as part of another partnership, government partnership initiative called the Natural Hazard Partnership, where UK government organisations are working together to provide this hazard information. And this is just one example of the work of that group. But also what we're doing is creating information for the specific responder community. And that's through the generation of what we call the Daily Hazard Assessment Report. And this is a report that goes out to the responder community, local authorities, police, fire and rescue on a daily basis at 2 o'clock, and indicates in that day or in the following days any potential geohazards that could affect various areas of the UK. And it describes them in terms of spatial areas, and we're just in the process of also generating maps associated with that. So, they're just a few of the key communication challenges that, through the work I've been involved in the last 15 years or so, have actually been developing and, in the last couple of years, advancing rather rapidly. But, like all things, we need to look to the future. And many of these things will continue in the future, but I think there are a few things that need to be highlighted as some of the future challenges we have. Ensuring engineering geological information is given in an appropriate and usable format, particularly, as I mentioned before in those examples, for the non-professional geoscientists, in the geohazard world, for urban planners and developers, is vital. Continued progression to ensure that information reaches decision makers and, most importantly, enhances knowledge of the subsurface and enables sustainable development of the subsurface is vital. And that continued work with the social and economic scientists to improve communication and ensure the value, most importantly, of the engineering geological data and information is understood and, most importantly, appropriately used. And I think one of our biggest challenges as a community is to actually understand and present to stakeholders that are non-specialists in particular how engineering geological data and information deals with uncertainty, and finding innovative and clever ways to actually visualize that so people can understand it. So, we need to build on our knowledge and ensure it is effectively and appropriately communicated. And that means we need to have, there's a lot of effort, there's a lot of development, and we need to have quite open minds. And it may mean that we even use such systems as Minecraft, and for those of you that have young children and teenagers, you'll know what Minecraft is, and for those that you don't, there's some information on our website about it. But using different tools to generate geological and engineering geological models to help people understand and comprehend our information. And it may even be that we actually use simple systems. And one of the most innovative ones I saw recently was using Lego. But it helps people understand. But the key is to help people understand also the spatial variability and the uncertainty. I'd just like to thank a number of my BGS colleagues that helped contribute to this talk, and also thank the resources that the IAG Commission 25 have produced on engineering geological modelling, and encourage you to have a look at the C25 IAG website. And just to say, grazie mille. Mm-hmm.